So we're going to revisit what liquids and solids and gases are. So the three states of matter is a table from your textbook giving some information about these. If we look at the density of liquid water and solid water, we see that those densities are approximately the same. And they're much larger than the density of water in the gas state, which we call steam. So here the density is much, much smaller. Molar volume is similar. It's related to the density, so it should be similar. The volume of 1 mole of liquid water is about 18 milliliters. For ice, it's 19.6 milliliters. A little higher, but still roughly the same. For water in the gas state, 1 mole of water would occupy 30.5 liters. That's a lot more than 18 milliliters. Why is that? Well, we can look at these illustrations here. In liquid water and in solid water, the molecules are touchingly close. They're very close together. In the gas state, they're very far apart. This is not even shown to scale. There's actually more space than is indicated in this illustration. But they didn't want to have to make a really, really big picture or really, really tiny molecules. So they exaggerated a little bit. So I said that intermolecular forces only are significant in short distances. So these are short distances. The molecules are very close together, and so the intermolecular forces are going to have an effect. In the gas state, the molecules are so far apart from each other that the intermolecular forces really don't have much of an impact. So there are some similarities between solids and liquids, but the difference is freedom of movement. So particles in the liquid, the particles are attracted to each other, but they have enough kinetic energy that they can move past each other. In a solid, the particles are vibrating, but they can't move past each other. So I find it helpful to think about Velcro. So think about people wearing Velcro suits, milling about in very close quarters, where you can't move without touching someone else, and they've got a Velcro suit on as well. It's going to be harder to move around, right, than if you're all just wearing regular clothes, or maybe even something very slippery. I don't know what that would be, but slime suits or something. So you've got this Velcro sticking to the other people, right? And so in order to be able to move, you kind of have to move a little faster, right? Because if you move really slowly, you're just going to kind of get stuck to each other. And that's really what's happening with particles in substances. You have a liquid, the particles can move relative to each other, but when you cool that down, lower temperature means lower thermal energy. The molecules are not moving as fast. Now you get to some point where they're moving slowly enough that they get stuck to each other, and that's when the substance freezes. Any questions? Liquids assume the shapes of their containers because the particles are free to move relative to each other. They're going to have a constant volume, but they'll take on whatever shape the container is. Solids don't do that. Gases also take on the shape of their container, but they are compressible, whereas liquids and solids are generally not compressible. So here we have a piston with a liquid in it, and if you put pressure on the piston, you're not going to be able to squeeze that liquid any closer together. All the particles are already touchingly close. This is the basis of a hydraulic system, like your hydraulic brakes in your car. You put your foot on the gas pedal. That doesn't operate the brakes. You put your foot on the brake pedal. I do know how to drive, actually. You put your foot on the brake pedal. That applies pressure to the brake fluid in the brake lines. And instead of the fluid compressing, it just transfers that force to the wheels where the brakes are. Gases, though, are compressible. If you've got a cylinder with gas in it and put pressure on it, you can squeeze the particles closer together because there's a lot of empty space. This isn't air between the particles. It's nothing, okay? If you have air in your gas, air in your gas line is a different issue. If you have air in your brake lines, your brakes feel mushy. You put your foot on the brake pedal and nothing really happens at first. You have to push too far. It's like, what's going on here? Well, any little air bubbles in your brake lines are gases, right? And so as you put pressure on it, the gas compresses. The force doesn't get transferred to your brakes until you finish compressing the gas. So there you have it. Brakes explained by chemistry. There are different kinds of solids. We've mentioned this before. Crystalline solids have nice arrangements, geometric arrangements of the particles. So here's an illustration of a crystalline solid. The particles are arranged in a particular order. There are many different structures that these particles can take, but they'll have a pattern. Amorphous, the prefix a means without. Morph refers to shape. Amorphous, without shape. Here the particles are just a big jumble together. There's no long-range order to them. We're familiar with state changes due to changes in temperature. This happens with water in everyday life. You take an ice cube, solid water, and you heat it up, and what happens? It melts and becomes liquid water, right? So as you're putting heat into this, heat energy, and you take it out of the freezer and you set it on the counter and you're like, I'm not adding heat to that. No, it happens all by itself because the air and the counter are warmer than the ice cube that came out of the freezer. And heat is a transfer of thermal energy from a warmer temperature to a lower temperature. So it absorbs heat, and that heat allows these particles to vibrate faster. So it's a little bit like maybe people in the subway and they're sitting in their seats, but they're getting antsy, right? You're adding energy, you're adding thermal energy, they're getting antsy, and eventually they're just going to get up and move around. Maybe they're going to panic or something because nobody will let them off the train. I don't know. You can make up all kinds of odd scenarios for that. But the particles get vibrating fast enough that they can start moving relative to each other, and that's when the solid melts. That temperature at which that occurs is going to be different for different substances. And it's going to be related to how strong those intermolecular forces are. If the intermolecular forces are strong, you're going to have to get up to a higher temperature before those molecules can break free and move around. If the intermolecular forces are very weak, the substance will melt at a much lower temperature. It doesn't take much energy at all to overcome those forces. Going from a liquid to a gas, if you heat the liquid, if you heat water on the stove, it eventually begins to boil. And if you wait long enough, you notice, hey, wait a minute, there's not as much water here anymore. What happened? Well, it's boiling away. It's going into the gas state, going into the kitchen air, and just floating away. Adding more energy to liquid molecules causes them to move around faster. And when they get enough energy, they can break completely free and get into the gas state where they're just independent, floating around, not relating to anybody else. So we're familiar with the heat changes. You can also cause a change from a liquid to a gas by reducing the pressure. And we'll talk about that later. If you reduce the pressure on a liquid, you can cause it to vaporize. With the gas, if you cool it down, it will condense. You can also cause it to condense by putting pressure on it. Pressure doesn't have much of an effect between solid and liquid. Any questions? So here's an illustration of an LP gas tank, like you might have in the backyard for your gas grill. It's filled with liquefied petroleum gas, which is mostly propane. So we talk about it as propane. It's not pure propane though. Liquefied petroleum gas. They sell it in a canister like this under high pressure, liquefied, because then it takes up a lot less space than if you were to sell it as a gas. And it will remain a liquid because it's under pressure. The pressure is pushing those molecules close together. When they get close enough together, they will condense into a liquid regardless of their actual temperature. There's just not enough space. You're forcing them to be a liquid. You connect this to your grill. When you open this vent, there are some molecules present in the gas state above the liquid. When you open the vent, there's a great deal of pressure in here. Those are going to escape. And then molecules that are in the liquid will replace those that were in the gas state. And as the gas comes out, you'll continually replenish the molecules in the gas state by the liquid evaporating. Any questions? Yeah?
Is that why when you turn on a grill at first, it's like a sudden burst because the gas escapes first?
Probably. When you first turn the gas on, it kind of goes whoosh,
Yeah.
right?
And then it goes to like a subtle.
And then it doesn't sound like much is happening. That could be also from the air getting expelled. You've got this sudden change in pressure, and so it's a little bit like a sudden acceleration, and so all of a sudden everything goes whoosh, and then everything is just continuously moving, and so you don't really notice it. Any other questions?